Hello everyone, thank you for coming to my presentation. The title of my talk is Identifying Critical Pedagogical Decisions Using Critical Reinforcement Learning Framework Based on Long Short-Term Rewards. It contains two works. The first one is about exploring long short-term reward in identifying critical decisions in a simulation environment, and the second one is evaluating it in an empirical classroom study. Intelligent tutor system is a type of highly interactive e-learning environment that facilitates learning by providing contextualized feedback and step-by-step support to individual students. It often makes a lot of decisions when interacting with students. To demonstrate it, let's start with a simple math problem. To solve for x in a typical ITS, the student will solve the problem step by step with a tutor's assistant. For example, this problem can be solved in 3 steps. First, multiply both sides by 3. Second, minus 1 from both sides. Third, divide 2 on both sides. During this process, the tutor can decide whether to show the steps to students or ask students to solve it by themselves. If a student gives any wrong answers, the tutor will give feedback. As you can see, ITS often make lots of decisions. That is a long trajectory of decisions with a goal of improving student learning. We believe that these decisions are not equally important, in that some decisions are more effective while others may not be so. Therefore, our research question is how to identify critical decisions that are linked to student learning, especially in a long trajectory of decisions. It is hard to define the critical decision directly, but it is easy to ask by comparing critical versus non-critical. By name, critical decisions are a series of decisions have a great impact on the desired outcomes. The non-critical decisions are those have weak impact on the desired outcomes. So now the question is how to identify critical decisions from non-critical ones. In order to identify critical decisions, our result shows that we need to identify critical states first and then to determine what is the optimal action on the critical states. This sounds obvious, but it is very important to separate these two processes in terms of evaluating critical decisions. To evaluate critical decisions, we propose critical policy, which takes optimal actions in critical states and any action in non-critical states. Intuitively, the more accurate the critical state is, the better performance the critical policy will have. To identify critical states, we proposed a critical deep reinforcement learning approach based on long short-term rewards. More specifically, the long-term reward is Q-value difference from RL-induced policy. Besides the standard DQN policy, we modified the Bellman equation to consider the criticalness of state, that the max Q value is considered in critical states, while in non-critical states, the average Q value among all possible actions is used. Finally, the short-term reward is the inferred immediate reward from InferNet model. Next, I will show the workflow of our critical DQN algorithm. First, we apply the short-term reward to identify critical states. The left chart shows the distribution of inferred immediate rewards in the training dataset. Based on the elbows, we have two thresholds, positive 0.5 and negative 0.5. To identify critical states, the logic is that for any given state, if any action can result in a large positive or a big negative immediate reward, then it is critical. Next, we apply the long-term reward to identify critical states. The right chart shows the distribution of the Q-value difference in the training dataset. It is important to note that the distribution is calculated based on the Q-values and the Q-value is updating iteratively. So our long-term reward threshold is a percentage in the ranking, like 50%, and the state with higher Q-value difference are critical. Finally, we apply the modified Bellman equation to update Q values until converge. Then we evaluated our framework on 3 test beds: an ideal grid-world game, and a real-world ITS dataset, and an empirical classroom study. This is the interface of the grid-world game. The goal of the agent is to collect as much reward as possible. In the experiment, we first collected the training dataset by taking random actions and applied the infinite to infer the immediate rewards. Second, we do offline learning to induce the CQN and DQN policy. Then, based on the 2 factors in the critical policy, identify critical states and select optimal actions, we have 4 critical policies. Finally, it's the online evaluation for the critical policy. This is the experimental result. The x-axis shows the long-term reward threshold, and the y-axis shows the average rewards received by the critical policy. Here, the 0 threshold means the policy always takes random actions, where the 100 threshold means the policy always takes optimal actions. There are 2 baselines indicate the worst and best performance. First, there is a general trend that the larger the threshold, the better the policy performs. In other words, the more states are identified as critical, the better the policy performs. Second, the red and blue lines are significantly better than the other 2 lines. It reveals that critical DQN is better than DQN in identifying critical states. When compare the policies used to select optimal actions, there is no significant difference between the red and blue lines, also the green and purple lines. It means that for selecting optimal actions, there's no difference between the critical CQN and the original DQN. Next is the experiment on a real-world dataset. This is the interface of our Pyrenees tutor, which is a web-based ITS for probability. To induce critical policy, our training dataset contains 1,000 students from 6 semesters. The state contains 142 features. There are 3 actions, and the reward is normalized learning gain. In this experiment, we applied per decision importance sampling to evaluate the performance of critical policies. This is the offline evaluation results. The x-axis is the long-term reward threshold, and the y-axis is the PDIS value. In general, the higher the PDIS, the better the policy performs. First, the general trend is still hold that the larger the threshold, the better the policy performs. And after 40% threshold, the blue line policy performs best, which applies the critical DQN to identify critical states and original DQN to select the optimal actions. In the first 2 experiments, we learned that critical DQN is better than original DQN in identifying critical states, but in selecting optimal actions, they perform similarly. And from the offline evaluation results, CQN-DQN is the best critical policy. So in the following classroom study, we will use this CQN-DQN as our critical policy. Next, we conducted an empirical classroom study to further evaluate our critical reinforcement learning framework. In this experiment, we proposed 2 hypotheses to evaluate the effectiveness of the critical policy. First, the necessary hypothesis is about whether it is necessary to carry out the optimal actions on the critical states. That is, on the critical states, if we do not carry out the optimal actions, then the performance would suffer. Second, the sufficient hypothesis states that carrying out the optimal actions on the critical states is sufficient. That is, carrying out the optimal actions on the critical states only could be as good as carrying out optimal actions everywhere. To validate these 2 hypotheses, we conducted a classroom study. To test the necessary hypothesis, we compared critical optimal policy which takes optimal actions on the critical states and any action on the non-critical states, against a critical suboptimal policy, which takes suboptimal actions on the critical states and any actions on the non-critical states. The only difference between the two policies is whether to carry out the optimal actions on the identified critical states. If the necessary hypothesis is valid, that is, for the critical states, the optimal actions has to be carried out, and we expect the critical optimal policy outperformed the critical suboptimal policy. To test the sufficient hypothesis, we compared the critical optimal policy against a full RL policy, which always take optimal actions on every state. If the sufficient hypothesis is valid, that is, as long as the policy takes optimal actions on the critical states, it is good enough. So we expect the critical optimal policy performs similar to the full policy. Next, I will briefly introduce the procedure of the classroom study. In this classroom study, students were randomly assigned into the three conditions. There are 4 phases in the study: pre-training, pre-test, training on the tutor, and post-test. Next, I will show the results. In the necessary hypothesis, we compared the critical optimal condition with the critical suboptimal condition. First, we compared the pretest and isomorphic post-test scores. For pretest, there's no difference between the two conditions. It means the two conditions are balanced in terms of incoming competence. Then the result shows that the isomorphic post-test scores are significantly higher than the pre-test scores in both conditions. It means that our tutor could improve students' learning regardless of the policies deployed. Then we compared the learning performance between the two conditions. The result shows that the critical optimal condition significantly outperformed the critical suboptimal condition on both isomorphic NLG and NLG. It reveals that different actions on the critical states have significant impact on students' learning performance, and thus optimal actions should be carried out on the critical states. In the sufficient hypothesis, we compared the critical optimal condition with the full condition. The result shows that there's no difference between the two conditions on students' learning performance. It indicates that carrying out the optimal actions on the critical states only can be as effective as taking optimal actions everywhere. In this study, the result shows that our critical policy indeed identifies critical decisions in student learning, and it also reveals the fact that on critical states, it is important to carry out the optimal actions, and carrying out the optimal actions on the critical states is good enough. That's all. Thank you.